what I did last time was talked about the Lorentz group. So I'll kind of quickly review that and say a couple more things I wanted to say about how to think about the Lorentz group. And then but most of what I want to do today is really go and talk about the Poincare group and its representations. And the idea is one of the kind of strange and unusual things I did in this class earlier on, especially in the first semester, was to try to talk about the theory of a free particle as in terms of the representations of the Euclidean group in 3 dimensions. So and one of the main kind of motivations for setting all that up in that way was that it's then relatively straightforward to go from the Euclidean group in 3 dimensions to the Poincare group in 4 dimensions. So I'll kind of quickly say something again about the 3-dimensional case, about what happens in 3 dimensions, and then what we're going to talk about and what you need to do to kind of go from non-relativistic theory to the special relativistic theory, but which you can think of as just going from the Euclidean group in 3 dimensions to this Poincare group. Okay, so let's see. So last time, okay, so last time what I did was really told you that the Lorentz group was, and I think it's fine. Okay, so the Lorentz group, and mostly when I talk about the Lorentz group, sometimes I'll mean the SO31, sometimes I'll mean the spin double cover SL2C, but mostly I'm actually thinking in terms of the double cover. So we'll think of it as being SL2C, which is 2x2 complex matrices with determinant 1. And what I wanted to, so we're not going to get into, we're just going to talk about finite dimensional representations of this, and it turns out that they're all, they're not unitary representations, but so they're going to be, so the irreducible representations are you're basically taking, let me call it this, BS1, BS2, and so this is etc. And let me actually put a bar here. And what these things are, as I explained last time, was they're just they're kind of the standard. You can construct them the same way you would the standard construction for SL2 representations of various spins in terms of homogeneous polynomials in Z1 and Z2, and you get the standard story about the different spin representations. And if you construct them that way, you don't just get SU2 acting. You get SL2 acting, SL2C. And then this guy is just, but the thing which is different about one thing that's different about SL2C from SU2 is that the complex conjugate. So this is going to be some for each group element, you're going to have some matrices. Here you're going to just have, you're going to take the same representation and just complex conjugate all the matrices, and that will give you a new representation. And in the case of SU2, that one was unitarily equivalent to that one. There was no real, they were just a change of coordinates. Here, this is actually something different. And so now so just as in the case of SU2, you could also think of that the really interesting thing to think about was the spin 1/2 representation, because once you knew what the spin 1/2 representation was, by taking tensor products of that with itself, you could get arbitrary spin representations. And so the same thing here is you want to the basic case to understand is what happens for if you put spin 1/2 here and then a trivial representation here and make this one trivial, or if you anyway take the spin 1/2 version of this and take this one trivial. So the basic case, and I called these are 0, 1, 0, and 0, a half. This is what I call this. And I call this also sometimes the left-handed spinors, and this the right-handed spinors. But so we're mainly interested, in some moral sense, once you've actually understood these representations, you can get arbitrary ones by taking direct sums and tensor products of these things. But then, you don't. This does get complicated. If you start taking tensor products of these things, you're not going to get an irreducible representation. You're going to have to figure out how it decomposes into irreducibles. But in principle, one can do that. So, and it turns out kind of physically, in terms of the physics of elementary particles, these are kind of these and maybe the spin 1 case are the crucial examples. Okay, so what did I? So let me see what I said. Okay, and then so I want to think about these things. It's also useful to we're going to sometimes want to think about the dual representation, the representation of linear functions and its dual. And this one. So I kind of went through these things last time, telling you what those, how to find, if you start out with this guy is the guy who's just the defining representation. If you want to know a group, the matrix that acts on these guys, the pi of g's here are just the SL2C matrices themselves, and then here they're just you take the SL. If you want to know what pi of g is for g in SL2 matrix, you just complex conjugate the SL2 matrix. Here on the duals, you always have to take a transpose inverse to get the dual action. Okay, then what else do I want to tell you about this? Then then the other thing I wanted to tell you about this was how this is related to Clifford algebras and gamma matrices. So let's see. Did the So in four dimensions, you can define with signature 3-1. You can define the Clifford algebra, and it's going to be given. It's an algebra of 4x4 complex matrices, and you can figure out what it is by finding four matrices corresponding to 0, 1, 2, 3, which satisfy the Clifford algebra relations. And so in these, one choice of these is this one. If you take so these are going to be 4x4 complex matrices, and you take them to be. I guess I always put a minus I here. You take the gamma 0 to be this. If you square this, you're going to get -1. And then the other ones for j is equal to 1, 2, 3. What you do is you take you use the Pauli matrices, and you can easily check that these are things that if you square them, you get 0. That's right, you'll get -1. These are things that if you square them, you'll get 1. The property is the sigma j squared. You're going to get a -1 from squaring the sigma j. It's going to cancel a -1 here. So these guys will satisfy. So you'll have gamma 0, 1, and then you'll have and then these things, and then different ones will anti-commute. That if you multiply any one of these by any other one, and then if you do it in the opposite order, you're going to get a minus sign. So that's the Clifford algebra for this one. But this is only kind of one. This is kind of one representation of the Clifford algebra as matrices, but it's the one which I think it is clearest for trying to explain how this group is acting. So let's see what else I want to take. Okay, so now what you can do. So you can also think of these guys as giving you. You can really think of this as being kind of a basis vector in the time direction, in the 0 direction. if you think of your Minkowski space as 2 by 2 complex matrices. So one kind of standard notation is to say if you've got some kind of element of Minkowski space, R V1, then you can identify these things with 4 by 4 matrices, and that's just V. And there's this notation, which is the Feynman slash notation. You just take, so it's the sum k is equal to 0 to 3 of ek gamma k. So you just take the coefficients of your vector with respect to this basis, and then you basically just use these guys as basis elements. And if you write this thing down, what you're going to get, let me see, it's going to look like this. It's going to look like 1 is I, and you're going to have a 2 by 2 0 blocks here. But then you're going to get here. You're going to have what is an x0 plus x3, and then what does it happen? What is x1 minus ix2? And then down here, so this is going to be this 2 by 2 block up here, and then down then here you have the same thing with x0. Let's see. So the x0 stays the same, and the spatial components change. So it's if you write it down, it's x0 minus x3 minus x1 plus ix2 minus x1 minus ix2 x0 plus x3. It's this guy. Yeah. So you can think of the gamma matrices as what they're doing is they're giving you this identification of 4-dimensional space with 4 by 4 complex matrices, which are your explicit realization of your Clifford algebra. But they're very special 4 by 4 matrices, and really what matters. I mean, once you know what this guy is, you know what this guy is. So all that really matters is this guy, and this is something which so this is so here we're just identifying. Anyway, I have to say we're identifying. Yeah. So if this has cut, anyway, this has I'm kind of using X and V's, but this is. Anyway, but all that really matters is this 2 by 2 block, and this is something which I kind of already talked about. So I already kind of early on when I was talking about Minkowski space, I was saying you could identify Minkowski space with 2 by 2 Hermitian.
Just have a question. Why don't you change the sign of x1?
Because where here? Oh, here. Well, here. Wait, so here it's. Wait, which sign of x1 are you worrying about? Which one? So this is just so that, I mean, haven't I gotten x1 is? Did I write this down wrong? It's quite possible I wrote this down wrong. So x1 is.
No, maybe just I mean in the bottom left side. So why don't you change the sign of x1?
X1. Well,
if there's delta 1 and negative delta 1, so why don't you change it?
But isn't this what I did?
Yeah.
What I was trying to do was just leave x0s alone and change the sign of the xj's.
So you have to change the sign of x1, but here there's no negative x1 minus plus x2 and negative x1 minus x2.
But isn't, I mean,
So
is
you
this,
change the sign for x2 and x3, but why don't you change the sign for?
but didn't I do this? Anyway, I'm not, I must have made, so there must be some mistake here, but I thought I did exactly that. Isn't that exactly this, or maybe is it not readable at the x1 here? Yeah, sorry. Maybe my writing may not be readable. Is that it? Sorry. So this is minus x1 plus ix2 and minus x1 minus ix2. Is that right? Anyway, sorry. I'm sorry. It may be my writing, may be a mistake, but yeah. But the important thing is that this is this is the old story I was telling you about, that you could think of Minkowski spaces as 2 by 2 self-adjoint matrices, right? So this is a 2 by 2 self-adjoint matrix, and then this should be the same thing with x0 left alone and the xj's with a minus sign. Right. Is that?
Well, I'm not very sure about that.
Which way? Where are you seeing a problem? I'm just not seeing it.
Well, just I'm not so sure. Maybe that there's a change of sign. Just I think.
Okay. Anyway, I mean, it's possible. Actually, maybe the thing to say is also, I think what I'm saying here should also correspond to what's in the notes exactly, and those have been checked very carefully. If you see, if the corresponding thing in the notes, if there's a problem, please let me know. I'll try to fix it. But I think this is right, but I'm not. I may be wrong. Okay. But anyway, the main thing is the idea that you've got so you've got these 4 real numbers which are telling you where you are in Minkowski space, and you can think of them, this Feynman slash notation tells you how to. Oh, sorry, I should have. Yeah, I kept. Maybe call this X to make this less. Okay, and then X slash. Sorry, yeah. So you're just identifying this four-dimensional space with certain very specific 4x4 complex matrices, but these complex matrices have a certain pattern that they're 2 by 2. They're really 2 by 2 complex matrices, and then some simple change on it over here. Okay. So you can think of this 2 ways. You can think of that that Minkowski space really should be thought of as 2 by 2 self-adjoint matrices of this form, or you can think of it that they should be thought of as the generators of this Clifford algebra in 4 dimensions, and then these generators are these kinds of 4 by 4 matrices. Okay, that clear? Okay, but now the thing to one reason, let me just say what I want to. So what's happening when you do the when you write gamma matrices this way is you end up then again when you take quadratic combinations of these things, they're going to give you block diagonal matrices here and here, and they're going to act on so the gamma matrices act on. So you've put together this. So you put together this representation, which is a C2, and this representation, which is another C2. You put them together into a C4, and the gamma matrices, what they do is they take vectors. So X vector, X slash takes mean, one thing it does is it takes this to this, right? Because if you act with this kind of matrix on something of this form, you'll take things in here, go to things in here, and then that's what this will do, and then this will take things in here to things here. So it gives you a linear. It takes linear maps S R SL, or if you like, that's the same thing as the tensor product. So this is one way of understanding how the vectors, in this way of understanding the world, and where vectors are 2x2 complex matrices, you can think of them as a tensor product of these two representations on C2. But I went through this more in last time, and if you take the what is it, that the quadratics in the gamma j, or give you, they give you things here, and this is the so this is the Lie algebra. But this is the well, that's right. On SL, this is okay. So when if you multiply any two gamma matrices, you're gonna get something that's block diagonal here and here, and and if you look at what those things are, like, you know, gamma 1, gamma 2 is going to be the thing which gives you an infinitesimal rotation action in the third axis, and that's going to be anyway. So you can work this out, and you can get the kind of Lie algebra version of the SL2C action on these two guys. And then if you exponentiate these matrices, you actually get group action. So if you actually want to I guess what this is saying is one way of constructing, you know, if you want to know that I'm doing some rotation about some axis, and it may also include boosts. It may include a rotation in the time direct, you know, in the kind of a time space direction. You just find the corresponding quadratic combination of the gamma matrices that will give you that, you know, that defines that plane you're rotating in, and then you've got that gives that gives you the actions on these two guys, and if you exponentiate these matrices, you'll get the group action. So what I'm really just trying to do is just try to make a connection between the Clifford algebra's point of view and just the kind of pure representation theory point of view on these guys. And it's really kind of going back to this kind of general principle that we went through at some point, that you really could, the way to understand spin representations was in terms of by using Clifford algebras, and by looking at the fact that that what you get by taking quadratic combinations of generators of Clifford algebras, and you actually get a Lie algebra, which is the Lie algebra of the spin group. Okay. So that's how this is working out here, very explicitly in terms of matrices. Let's see. Is there any? But is that? I mean, this is a little bit of a tricky story, but it's But yes, but are there any questions about this? I mean, is this relatively clear? Okay. Anyway, so it's a combination of some special properties of what's happening in Minkowski space and in 4 dimensions, and so these this kind of nice story about 4x4 matrices is something very special to the kind of spin representations in 4 dimensions. Okay, let me then go. So this was more kind of intended review of last time and what is in the what's in that last chapter. I think there are a couple things. Let's see. I can say there are a couple things about that I didn't get that I should have said last time. Okay. Yeah. Just a few things, which is this. So another kind of standard thing to do is so you also define gamma phi. You can define a special 4x4 complex matrix by taking I gamma 0, gamma 1, gamma 2, gamma 3. So if you multiply all of the Clifford Algebra elements together, so you get this, and then what you're going to do to calculate this out, you get minus 1, 0, 0, 1. So, you know, if you're working in this if you decide to work in this formalism with gamma matrices and the Clifford Algebra and the Clifford Algebra, then what you need is you need some way often of projecting of picking out the separate SL and SR star pieces, and that's the so this implies that if you use 1/2 1 minus 1 minus gamma phi projects on L and 1/2 1 plus gamma phi projects so one kind of standard formalism for doing all these calculations is just to work with C2 spinners, but then you have to keep track of the fact that there are 2 kinds of them, these guys and these guys, and then you can do this with you have dotted indices here, undotted indices here, and undotted indices here, and dotted indices here. That's one formalism. The other standard formalism is to work to put these together and work with 4-dimensional work with your standard. The way you talk about spinners is in terms of 4 complex dimensional things, and so you put these together into a 4 complex dimensional thing, and then you do everything with gamma matrices. But if you do that, then then sometimes you need to somehow project onto these things which behave differently under the Lorentz group, and the way you do it is just with these projection operators. Okay. So this is more of a standard. If you look at the kind of standard calculations in a typical quantum field theory textbook, this is what they're always using these operators to kind of project out onto these so-called chiral. These are called chiral spinners, as they've got a certain handedness. And so you're often projecting for what are often called Dirac spinners, which are the 4 complex dimensional ones onto these guys. Okay. So that's one thing I wanted to say, and then just the last thing. Let me not. I think I'll get to this later on when we talk more about actual theories of spinor fields. But there's the other thing to notice is that there exists there exists a choice of gamma matrices that are all entries real. Okay. So you can work with there is something that's very, very special to this kind of Minkowski space 3-1 signature, is that you actually can you actually have the fact that Clifford. So the Clifford algebra of signature 3-1 before you complexify, the real Clifford algebra is 4x4 real matrices. So this, so it's isomorphic to this. So there is a way to do this, and this is called the Majorana representation. And I'll say something later on when we get to talking about theories of spinor fields. I'll talk about what happens if you try to what you can do with this Majorana representation. But the anyway, but that's another story. Okay, so I think that's pretty much everything I wanted to tell you about the oh, and then the so now your spinors are 4 spinors, and then but what happens is if you take these guys and then complexify, so you have a representation of spin 3-1 on, which is a real representation, not the kind of representation we normally have been thinking about representations on complex vector spaces. You actually have a representation of spin 3-1, a real spin 3-1 representation on this guy. But if you complexify, look at the complexified representation, that's a representation on C4, and that gives you back the Dirac combination of these two C2s. So this is R4. You complexify, you get 4 C4, but it comes out as a C2 and a C2, and so this is actually another argument about why you might want to think about why you might want to combine these two things into a 4-dimensional thing, is because they are the complexification of a real. There is a real story underlying the whole thing, which when you complexify gives you this guy. Okay, so that maybe let me kind of get off of that and get on to what but maybe I better. So is there any other questions about Minkowski group or the Minkowski representations? I mean, or the SL2C Lorentz representations? I'm gonna move on now.
So your projected form here is R31. So and you have gamma 5 and I remember when we were talking about the Clifford algebra, we have a question that gives a big gamma matrix, which has similar form. So I mean, for other kind of projected form like R22, R13, something, well, I don't know. So you have similar results like the gamma 5, gamma or something.
Yeah. So there's a tree. There's a complicated story about So you can always write this down for any Clifford algebra in any dimension. What you could do is you can take the product of all of the gamma matrices, and then you get something which has an interesting behavior that you can get it to anyway I think in that problem in your problem set, then you saw some of the properties of this. So yeah, that's the same gamma 5. So but then the what this gamma 5 tells you depends kind of subtly upon upon the signature, and also like whether you're dealing with these real things or these complex things. So what happens, for instance, in this guy, so yeah, so one way of thinking about how you want to split up the spinors is that what you want to do is you want to you're looking for a matrix representation in which this guy is diagonalized. So I mean, if somebody gives this to you, just it gives you some other version of the gamma matrices which satisfy the same relations, but that they're in a completely different basis. then one way of saying that what I want to find, what this is doing, is whatever this guy is, I want to diagonalize him. The whole point here of this particular version of gamma matrices I've used is that it diagonalizes this guy. And this is kind of why this is the special property of the gamma matrices I'm using, is that they diagonalize gamma 5. In some other representation of the gamma matrices, gamma 5 will be some other thing. And if you want to recover these guys, you have to change basis and diagonalize it. And then one of the aspects of this story is that you can't diagonalize this guy over just using real numbers. It turns out you need anyway. So there's one of the basic facts about the story in 4 dimensions is that you can't simultaneously work with real spinors and get gamma 5 in this representation. So it's actually, did I write down? Anyway, so another way of saying that is you can go and look with this Majorana representation where you have 4x4 matrices, and then what happens is that you can compute gamma 5, but gamma 5 is not going to be diagonal. So you so you can't, over the you can't break up real spinors into two real pieces. You have to complexify in order to be able to do this. But I don't know. But this gamma 5 is exactly the one that was in your problem set before, yes, and it should be. So the properties you're being asked to show there should be consistent with what I'm saying here. Is that right? Okay. Anything else? Okay, let's go on to the Poincare group now. So maybe before we get to the Poincare group, let me first kind of review the Euclidean group. Okay, so the Euclidean group. So this was, we had E3, R3, the minor product of SO3. Or we might also be interested in using spin3 here, taking the double cover, but I won't distinguish that. And then what we found is that to get representations, okay, so the representations of this guy are infinite dimensional, the irreducible representations, and that's the way to get them. They're kind of two way. There are several different ways of doing this. One thing to do is to use the Casimir, is to construct these. There's certain quadratic things in the Lie algebra which when they act on a representation, they commute with everything, and they're called Casimir operators. So you have two Casimir operators, which was P. I'll say P1 squared plus P3 squared, and then J vector dot P vector. Okay. So one way of trying to think about what are the possible irreducible representations of this guy was to realize that there were these two, that you had these two operators. So whenever these P's are the infinitesimal generators of translations. So the fact that you can do infinitesimal translations gives you an operator P in a representation. The fact that you can do infinitesimal rotations gives you a J. And then you got these two operators, this guy and this guy. And then what we found is that you could classify representations by the eigenvalues of these two operators. And so this guy gave you just the inner. So anyway, so you could do this in terms of anyway. So you see, this was one way of classifying representations, was in terms of the eigenvalues of these two operators. Now, let me not I'll say some more in a minute. Or look at orbits of the SO3 reaction on the momentum space, which was the space of characters on characters of R3, and you can think of that as just a dual space of R3. These orbits were anyway. So R3 is just R3, and so the orbits are just are R3, and these are spheres. Of some radius r, let's say, and but it turns out that this operator is just this is the operator that computes the radius squared in momentum space. So this is equal to the this r is if you take it to any vector here and look what happens when you act on it with S of anything in here, and look at what happens when you act on it with SO3, you get a sphere. That sphere has a certain radius, and that radius squared corresponds to knowing this Casimir. But the other thing that happens is that if you pick some particular vector on here, then there's some subgroup of SO3 that leaves this vector invariant. So you have kind of you have rotations about the so you get it for each vector, P vector, you get a subgroup of SO3, which is an SO2 of rotations about the vector. Okay. And so this is called the stabilizer for each element in here. This is called the stabilizer subgroup, or the little group of this point in this space. But the space is just the space of momentum. Okay, and so then the representations are characterized, it turns out, by how this SO2 acts. And so the representation of SO2 is it turns out infinitesimally it's given by this guy, and this is called the helicity. Okay. And so this is the infinitesimal. This is kind of explicitly the component of the action of rotations in the p direction. So it is the rotation. It's really, of course, this is the thing which generates rotations about this vector. So anyway, there are two different ways of then kind of characterizing irreducible representations. One is by what the eigenvalues of these two operators are, and because they commute with everything in the Lie algebra, they act as scalars on irreducibles, and so you get two scalars, or you can also think of those two scalars as characterizing first this orbit and then the behavior under the stabilizer group at any particular point in the orbit. So this was the this was kind of the general story, and there's a similar story that you could do in any dimension. If you try and go to higher dimensions, you just find that the story about stabilizer groups and their representations gets more complicated, and the story about Casimirs gets more complicated. But it's the same philosophy. So this was the abstract representation theory, and then more concretely, So this tells you how to classify representations, but to construct, oops, what you do is use, look at, so you consider there are free particle wave functions. Valued in Cn, and then so the first Casimir. So the anyway, and then what you do is you have the group acts on. So E3. Let's take it. You know, you're translating by some vector, and you're doing some kind of rotation. Acts on. So these take so you have psi, let's say psi I, which is your psi things that they're functions. Let's say L2 functions on R3, but then tensored with some Cn. So if you want to construct the simplest version of E3 representations, what you do is you take you just look at complex valued functions on R3, and you look at and then you say, well, my first Casimir is just the sum of the of p squared, but p squared over 2m is the energy. So having a fixed Casimir is just means having a fixed energy on psi. Well, okay. So let's take the simplest case. What is it? You want the well, it's a vector R inverse acting on X vector. So it's the inverse of the usual E3 action. This is the standard thing out when you induce from the action on R3 to the action on a function. So more generally, what you do, so this is what you get, like, just for single component wave functions. If you have multiple component wave functions, what you can do is you can take psi of x vector goes to some representation of the rotation of S. Pick some representation. Let me call this. Pick some representation of SO3, and then on Cn, and then act this way. Sorry. Okay. Anyway, so you know. So what you could do, and this is typically like what you do with if you're trying to describe a spin 1/2 particle. You take your size, take values in C2, and then the way the Euclidean group acts is that it acts by the usual action, induced action on the functions in the space, but you also have to use the spin 1/2 representation here also to get kind of to get the spin component to get the action on this factor. Okay, so I mean this is, I don't know. This is maybe, I hope it's not too confusing, but this is kind of a piece of a long story which I went through, and the idea is that the philosophy here is that what we're doing is we're all that I gave you before was some kind of general theory saying how to, what the classification of representations was going to look like, but it didn't tell you how to actually make them, how to actually build these representations. And what I was telling you here is that for E3, you can build these representations by just looking at the theory of a free particle in R3, the quantum theory free particle. But if you want anything more than these simple helicity zero representations. If you want higher helicity representations, you have to take wave functions that are kind of have n components, and you have to act. You use an action by the on those, and take some representations at SO3 on n-dimensional representation of SO3 on there, and also use that. So this is more kind of telling you how to actually go about explicitly constructing such things. Okay, so this was meant as all kind of a review of E3. So now what I want to do is I just want to take so E3 now is going to go to what's called the Poincare group. And I guess we'll just call it. Did I call it something else other than P here? Okay, yeah, I guess I call it P. Well, P, and so that's going to be R31. SO31, or maybe spin 3. Actually, let me start again with how's the. That's all right. Okay, so all I'm doing is really I'm just generalizing the story on E3 where this I'm putting an extra dimension in here, and it's as far as the translations are concerned, the fact that one direction is different as far as it's concerned doesn't make much difference. So the translate now you have 4 translations instead of 3 translations, and you have okay. And you have this group, which is what we've been talking about for the last couple lectures. So you've got this instead of SO3, you've got this guy. You've got either SL2C or SO31. But it's really the same story. It's just this guy, these guys act. Anyway, these guys act on these guys. So you can think of this as being in a group of translations, but you're not just putting together translations and rotations because your rotations are acting on the translations. So that's why it's a semi-direct product group. But it's exactly the same story as for E3. But it just anyway, just kind of one dimension up. Okay. So now maybe let me kind of So then there's the story about the Lie algebra of the Poincare group is very similar to the story about the Lie algebra of E3. So let me just kind of quickly say that. So let's just write down a basis. The algebra of the Poincare group. Well, what's it going to have? It's going to have infinitesimal translations. And these are just I guess that's called T0, T1, T2, T3. And this is just, and these things all commute with each other. All commute, and then the bracket of any of these guys is 0. So that's just the standard story about just translations in 4 dimensions. But then you're going to have infinitesimal rotations. And these are going to be just the standard thing that you're used to. This L2, L3. So this is a basis of the Lie algebra of SO3. So these are so the commutation. Now the commutation relations of these things, these just have the standard kind of commutation relations with themselves. L2 is L3. just the same story. And then the commutation relations with these guys and these guys. What's going to happen is that all of these are going to commute with T0 because spatial rotations don't spatial rotations don't just leave this alone. And then they're gonna act on these guys. It's going to be the same relations that you have in E3. That you're just the SO3 rotations act on the spatial directions. So this is so really so far nothing new has happened here except you've added in this guy. But the really new thing that happens is that you have these boosts. And I think I wrote them down. These are K1, K2, K3. And you have to worry about what those. So you want to know what the anyway. And I think I won't write. So okay. So what happens with these guys is they I have a formula. Anyway. Well, anyway, so I wrote down the. So what happens if you put these three guys and these three guys together? Then you've got the six-dimensional thing is the Lorentz group, and you've already and so we talked about that before, and so you get these the commutation relations are that if you take the Lie bracket of two boosts, you get an infinitesimal rotation. So the Lie bracket of two things in here gives you something in here. This is a subtly algebra. It just bracketing things in here stays in here. But if you bracket things in here, you get something in there. You know, if you want to kind of split these things up into two separate things, you have to complexify. And you know, if you start taking complex coefficients, you can split this up into two independent Lie algebras. But if you don't do that, then you have this sub-Lie algebra and then this Lie algebra of guys, which if you commute them, you land in here. And then you also have these guys acting on here, and these guys act as kind of infinitesimal rotations on here. So like what K1 does is it does an infinitesimal rotation in the 0, 1 plane, and K2 is an infinitesimal rotation in the T0, T2 plane, etc. So you can work out precisely what all the commutations relations are, and then that defines exactly the Lie algebra, the Poincare group. But they really are. That's really what they. Anyway, it's just the infinitesimal version of this group, and it's got ignoring the boosts. It's something you already understand. Really, it's really E3, but then it's got extra gadgets which rotate the T0s into the other three, and has this weird thing that if you take the infinitesimal, you take the bracket of two boosts, you get a rotation. That's the Lorentz story. Okay, so now I want to. Okay, now what about representations? How do I want to? Okay, so now what we want to do is, okay, so what about usable reps of heat? This is a question I want to get at. Now, so what you can do, one way of doing this is you can construct them using wave functions on R3, K1. With the and then the action in the same way as for E3. Let me just say So psi of x goes to some of this psi g inverse. So it's going to be the so one thing you can do is you can find some multi-component wave functions on not on three-dimensional space but on four-dimensional space, and then you then you just use the induced action of the Poincare group on the space to get to act on the functions, and then you take you have these guys valued in some representation of the Lorentz group, one of these finite dimensional representations, one of the ones that we just discussed last time and earlier, and then you use the representation of the Lorentz group of one of the ones that I talked about before, and then what you do is just in the E3 case, you had some kind of you had some kind of operators, which some kind of equations of motion, and you were looking at the action like on the solutions of a Schrodinger equation. So you had some operator acting on these things, and your operator was invariant under the action of E3, and so it commutes. So that operator and the group action commuted. So you could look at the solution space of that operator, and that would give you the irreducible representations. That was kind of what you did. So the general story, which we're going to get into, we're going to see a bunch of examples of later, is really if you actually want to construct these things, what you're going to do is you're going to find some operator, which is a generalization of the free particle Schrodinger operator, but which is appropriate to 4 dimensions, not to 3 dimensions. And you're going to look at you're going to choose it to be Poincare covariant, so it commutes with the action of the Poincare group, and then you're going to get the Poincare group action on solutions of that on the solution space of that operator, and then that's good. That's how you're going to actually construct these things. So I'm not actually doing any of this yet, but I'm just saying that's what we're going to kind of see later in the class. So later in the class, I'm going to try to actually construct these examples of these relativistic quantum mechanics, relativistic quantum field theories, but they're going to be what we're going to try to do. But before I get to this, what I can do is I can use this very general nonsense about how to classify the possible things you're going to get. So we can go back to the classification theory. Classification theory of the era. Well, so the first way to do it is to find is to pick out find the Casimir operators, and so in this case the Casimir operators are the so here it's going to be a. Well, the first one is going to be P. But just what you do is instead of taking this guy, so this is what you had in R3. This acted on functions in R3. This is basically the Laplacian in 3 dimensions. But now we've got functions that are functions in of x1, x2, x3, but also x0, and we want to find an operator which is invariant under the action of the Lorentz group. So what you do is you just add this. So and then it turns out that all the calculations that you were doing involving SO3 and functions on R3, it becomes the same, and showing that this was an invariant operator. You get the same calculation, except now it's SO3 1, invariant instead of SO3 invariant. Same story. And so this is going to be our analog of the energy operator p squared, which was p squared over 2m for the free particle Schrödinger equation. And I'll start talking about this next time. We're going to, instead of looking at, we're going to look at functions of R31, functions that are also dependent on time, and then we're going to take our basic operator to be this guy, but we're also going to throw in this guy. And you can think of this as being kind of the first Casimir. So it's the first Casimir. Then the second the story behaves just the same as in E3. So to find irreducible representations, we're going to try to find this operator is going to act on all our representations, and we're going to look for representations with a certain eigenvalue of this operator. Okay, but then the second one is kind of tricky to write down. It's let me just write it down. I'm not going to try to. So the second one it's called the Pauli-Lubansky. Well, first you have something called the Pauli-Lubansky operator. What you do is you take a four component object where the first component is basically this is the thing which you were using to get the helicity in 3 dimensions. This was the second Casimir in 3 dimensions, but you put it together with the vector with this somewhat mysterious thing, E0 data vector plus Q vector plus K. And then this thing you knew, if you're just thinking about 3 dimensions, this guy was an operator that had interesting characteristics. But it turns out that this is the right, if you want to have something which kind of behaves nicely under 4-dimensional transformations, you want to associate to this guy, and then even better, you want to then define. You get a second Casimir, which is this guy, which is W squared, which is this guy, minus sign. It's minus this guy squared plus these guys squared. And again, the reason for kind of writing the calculation of this structure is this makes it easy, or relatively easy. It's still a slightly tricky calculation to show that this guy is that this guy commutes with everything in the Poincare algebra. Okay, so it's fairly easy to show that this guy commutes with everything in the Poincare algebra, because, but it also is true that this guy commutes with everything in the Poincare algebra, and so he's a and he has inside him the second Casimir from 3 dimensions, which we already knew about, but he's a new one. But anyway, so I call this maybe P squared. But so one of trying to figure out what the possible representations are is to figure out what are the possible eigenvalues of P squared and of W squared. And if we can find the possible eigenvalues of these guys, then each choice of an eigenvalue here and an eigenvalue here will give us a different representation, and that you can try and get at the irreducible representations that way. Okay, but this is kind of hard. This is pretty easy to see what this is going to do. But let's go to the second method. The second method was the method of orbits that I talked about last time. So the second method is orbit. Okay, so if you want to understand what the what are the how do you, what are the orbits of the action of SO3 on R4? I mean, there's a dual, and in some sense, this is the space of characters is the dual, but I mean that doesn't really matter. But but you just use that SO3 acts on R4, and this is just the way the Lorentz transformations are acting on the possible values of the momenta. And so what happens is if you now in 3 dimensions, we could just think about R3, and we could look at how SO3 was acting, and if we took some fixed vector, it just moved it around in a sphere. Now the problem with thinking about R4 is that you've got 1 extra dimension to think about. You have to think about 4 dimensions, which is a little bit hard. But you want to ask, how does this group act on points on R4? If I pick something about a point in R4 and I act with this, what's it going to give me? Well, the way to think about this is really to take to just pick out 2 directions, and so maybe take this to be the 0 direction and this to be the 1 direction or something, and then the other directions are going to involve kind of a rotations in 2 dimensions outside of this, but we can classify the orbits by seeing what happens in the 0, 1 plane. And so let me give you the so the picture is this. Okay, so now if you start out with a vector here, and so this is going to this vector is going to correspond to, let me call it M 0, 0, 0, and then now if I act with this. If I act with this guy, so what he's going to do? It's going to be the action by boosts. You're going to take this guy and so rotations in the so the rotation group, the SO3 subgroup, just leaves this guy alone. It doesn't do anything to this because it's 0 here. So rotations just so this guy is invariant under rotations. SO3, but the 3-dimensional boosts move him in a hyperboloid. Okay, so they're going to look like that, and then you get the same thing on minus M. You're going to get something that looks like this. So then, if you want to know what the other dimensions are doing, if you took 1 dimension out of the plane here, you would just get a, this thing would just become a hyperboloid, and behaves like this. In the other dimension, instead of a circle here, you get your sphere. But this is this is what the orbits are if you just start with some non-zero vector in this time-like direction. Okay, and so let's just say the orbits of the first ones. So this is the first kind of orbit. So you get one kind of orbit is M 0, 0, 0. These guys, and then the stabilizer group. So the stabilizer group is the group exactly things which leave this alone and don't change it. Well, it's going to be exactly those rotations. It's going to be SO3. Okay, so the actual rotations, they leave the time direct. They leave the time direct. They don't do anything in the time direction, this. And so what you expect is but these guys, this m is really kind of the analog of the radius of the sphere. So you can have different values. You can have different values of m. And so these are classified. So you have two. So that you have classified by m. And then remember that what I said is that then you had to take a representation of the stabilizer. And the representations of SO3. I mean, I probably should be working with spin 3 or the spin. S. Spin S. Okay. So the one set of orbits are these things are these guys, and these are going to correspond to positive energy. These are going to correspond to negative energy, and so you're gonna there's going to be an interesting story about how you anyway how you do this, but these are these are you have positive energy orbits, negative energy orbits, and you expect your representations to be characterized by some number m and some spin s, and this is going to correspond to massive relativistic particles. So massive relativistic particles are going to be irreducible representations of the Poincare group, and they're going to be characterized by a mass and by a spin. Okay, then the second one is the other thing you do is the other thing that you have a light cone. You have things. You have all the vectors of the zero length, which is the so-called light cone. And if you pick some vector here on light cone, so let's take this 1, 1, 0, 0. If you take something on the light cone, let's see what are we going to have. Okay, then you're going to have another orbit. So you're going to have the orbits of 1, 1, 0, 0. This is going to be so. If you look at what's going to happen, this is good. You're going to get the you get the positive or negative light cone. So it's going to be kind of the degenerate thing of these hyperboloids are going to kind of degenerate to some kind of to something that looks like this, and has got also some. So you think of it as a cone going out, but it's got another dimension besides the dimension that you could see here. Yeah. Now the somewhat tricky thing here is what the stabilizer group is, and I don't have much. I maybe say a little bit more about that next time. But the interesting fact is the stabilizer group. If you ask, you say, look at what is the subgroup of the Poincare group that leaves this guy invariant? Well, it turns out he's actually E2. He's actually the Euclidean group of conventions. He's R2 and SO2. Okay, so now if you want to know what the irrets, well, what they we often say that they correspond to mass 0, that their m is equal to 0. They're kind of the massless case. They're the m is equal to 0 limit of the massive things, and so these are going to correspond to massless particles. It turns out, and this is the value of the first Casimir. But then then what you want is that they're supposed to be classified by the irreducible representations in the stabilizer group. Okay. Now remember the irreducible representations of the stabilizer group of E of 2. These really corresponded to there were the things corresponding to R2 acting trivially. There were the kind of zeros here, and then SO2 was some integer. And then there were the non-zero things, which corresponded to an orbit that was a circle. So there was some non-zero radius squared of this circle, and then the stabilizer of a point in the circle was trivial. So these were classified by the they're either a, let's take integers. This corresponds to the radius equal to 0 case, or B, R not equal to 0. And then they're infinite dimension. So there were infinite dimensional representations of E2, of course, and they really corresponded to kind of functions in the circle. But the kind of finite dimensional ones were the ones that corresponded to 0 radius, and they were just given by a choice of representation of SO2. Okay. So what the so these guys are going to correspond. Well, these guys are going to correspond to massless, this integer helicity. So that's what these guys are going to correspond to. And so this is one thing you know about. We're going to see, we're going to be able to write down theories of massless particles, relativistic massless particles, and they're going to have, they're not going to be classified by a spin. They're going to be classified by an integer, the helicity. And if you want, you can go back and try and figure out what that integer is going to correspond to a value of the second Casimir, and you can compute that if you want. Okay, but now so the problem with this is all the examples we know of that correspond to actual physical particles that make physical sense. I mean, there are other representations. So let me write down them kind of unphysical. There are irreducible representations of the Poincare group, which they're infinite dimensional. We believe from this classification theory that they should exist, and there are ways of actually going out and building them, but they don't actually correspond to any kind of physically sensible particles. And the first ones are going to be, so one is going to be these guys. Let me just these guys. So massless, and these things are called continuous spin. So I mean the analog of the anyway. So this is just a name for what these guys are. So people have actually periodically played with these objects and try and make physically sensible things out of them, but I don't think that's ever really been completely successful. So these massless continuous spin ones, which correspond to this, they correspond to these orbits of the E2 stabilizer group. Then there's two. There's, I guess, if you took this guy here, take a space-like vector, like take 0, 1, 0, 0, and then now look at the orbits of this thing. You'll get something like this, and it'll go around here, and go like that. So it's going to be a really kind of this kind of. So this was a 2-sheeted hyperboloid. This is a 1-sheeted hyperboloid. the problem is that this guy has a nice, the relationship between energy and momentum is the one you expect. This one gives you the energy and momentum relationship that you would get for tachyons. So this is a tachyon. Just a second here. So this is so these are what this. If you try to make sense of what's a tachyon, what is it? Well, we know precisely what it is in terms of representation theory. It's the irreducible representation of the Poincare group corresponding to these orbits that are the orbits of a space-like vector. The problem is that there's no way to split these guys. We can split between positive energy, which is bounded below, and negative energy, and there's something we can do to make sense of this. These guys have no splitting between positive and negative energy. We don't know how to make sense of that. And I guess that's that. Yeah, and I guess that's it. Yeah. And these guys, you can actually figure out the stabilizer group is SO21, SL2R. So again, if you try and make sense of these, it's kind of, you have to associate, not just, you have to associate kind of a space-like version of the mass, and then you have to associate an irreducible representation of SL2R. But these SL2R, these unitary irreducible representations of SL2R are infinite dimensional. So there's a lot of, so if you try and make sense of these tachyons, you have all sorts of, there's all sorts of interesting structure, but it doesn't seem to look anything like physics. Okay, maybe I should stop here.
Professor,
yeah.
I remember that we have done a question, problem last semester saying that the Lie algebra of E2 is the limit of the algebra of SO3. So,
yeah.
so here the stabilizer group of Lie is E2, and the stabilizer of, for example, M000 is SO3. So
yeah,
that kind of way saying that.
Yeah, I mean, that's actually related to this. So one interesting thing about the story is, so this is really the story of relativistic massive particles. The light cone is the story of relativistic massless particles, but it's true. So you can ask this question about, if you have everything that you're doing with a massive particle, what happens as you take m goes to 0? You're right. And you're right that the one thing that happens is that the stabilizer group, which is SO3 here, goes to E of 2 as you take the limit. So as you're taking the mass down to 0, and you're getting a more and more of a massless particle, you're getting something that looks more and more like the light cone. And but there's kind of a jump in behavior. I mean, the stabilizer group here, it's always SO3. The stabilizer group here is E2, and they're different groups. So something kind of discontinuous is happening as you go to m is equal to 0 limit, and you see this at the level of Lie algebras. The Lie algebra of the stabilizer group here, which is SO3, goes, you're taking this. You're deforming this thing, and there's some limiting object which is a different Lie algebra, which is the Lie algebra of E of 2. But yeah, but you're right. It's exactly the same. What you're asking about is exactly the same calculation for taking the m, looking at the stabilizer groups and taking m goes to 0 here. Any other questions about this? Okay, so again, I guess better let me stop now, and yeah, so I'll be around for a while. Yeah, so if you have any questions about this or anything else, or you want to start talking now about your project, you can connect back in a few minutes. Okay. Okay. Bye for now.
Thank you.
Thank you.